Welcome to the finally established second session. We have gained some more information about what's going on here, but not a complete solution. Dapeng is the first speaker of the session, and will need to stand here to do it for being the camera. And he's going to talk about library-based compartmentalization. Dapeng.
Okay. Good morning, everyone. My name is Dapeng Gao from University of Cambridge. I'm a PhD student of Robert Watson, and today I'd like to talk about library-based compartmentalization, which is my PhD research topic. So to motivate compartmentalization, we consider common sources of vulnerabilities. One is programming errors that compromise data and control flow, for example, buffer overflow. The other is logic bugs, so you do not necessarily have programming errors, but you've probably failed some security checks, which causes you to open files that you're not supposed to open, for example. And this is essentially an abuse of ambient authority. So one good way of solving this problem or mitigating them is to divide your application into compartments or domains of isolation. And there are many existing fault isolation techniques that prevent privilege escalation of compartments. For example, there are process-based solutions that use virtual memory and operating system access control. And there are language-based solutions that use a programming language with well-defined safety properties, like WebAssembly, for example. Now, all of these solutions have performance overhead or disruption to source code, which might hinder adoption. So our question is, can Cherry offer an alternative? So we came up with this model where we take advantage of capabilities. So remember, capabilities are unforgeable and monotonic. So in order to prevent privilege escalation, we just need to ensure that untrusted code gains only capabilities that they necessarily need. This is the principle of least privilege. So this limitation applies not only to capabilities that are reachable via memory load, but also more abstract capabilities that might be returned from system calls like mmap or open. So we treat in our model, we treat each dynamic library used by the program as a compartment. We do this because of two reasons. First, most untrusted code is commonly shipped as dynamic libraries. So in common software development flow, programmers download source code from third-party vendors, and they compile it themselves and then link them with their own application as a dynamic library. These third-party code is not necessarily trusted, so I think we can compartmentalize them to prevent them from gaining extra privileges. Moreover, we can, in theory, do finer-grained compartments, but they incur more disruption to source code, and you sometimes need static analysis or some runtime enforcement to do that. This is currently out of the scope for this talk. So this brings us to library-based compartmentalization, and I will state the threat model here. So the threat model is that your dynamic libraries come in ELF files, and we assume that the ELF files themselves are well-formed, because the runtime linker will need to parse the ELF files, and of course we can even harden the runtime linker to make sure that even malformed ELF files can be parsed, but this is also currently out of scope. Now, we assume that the ELF metadata follow appropriate security standards. For example, you don't map code that is executable and writable at the same time. So this can also be checked automatically, but still it's currently not implemented. Now, the most important thing about the threat model is that the code can be arbitrary. So as soon as the ELF file begins to execute, we can assume that anything can happen. The attacker can execute arbitrary code without any limitation. They can make system calls and do anything, basically. So I think this is a reasonable assumption because most untrusted libraries, the code is untrusted, but still you need to compile it yourself. So we basically treat the toolchain that you use to build the L files as a TCB. Now, as an extension, we can also group several related libraries into the same compartment to improve performance, because then you can save the cost of transitioning between all these libraries, because they are logically in the same compartment. So what is the scope of this work? What sort of software does library-based compartmentalization apply to? So we focus on executables and libraries that use libc and that interface with each other via C. And a natural question is, what about C++ programs? And C++ programs should just work subject to limitations in the current implementation. For example, C++ exceptions currently do not work, but if your program does not have exceptions, then they should just work. The harder question is security guarantees that we can provide to C++ programmers, because the security vocabulary that we use do not include C++ concepts such as virtual methods or inheritance or objects. We are just talking about functions and memory buffers, pointers. We don't talk about C++ things. So it's unclear what the security implications would be for C++ programmers. Now, if you just think of a C++ program as some kind of C program with lots of syntactic sugar, then you can sort of give a security model, but I think most programmers will have stronger ideas about the concept in C++. So it's currently also not, it's future work. Okay, now let's dive into the kind of protections that we can gain with library-based compartmentalization. And let's analyze the ways in which a piece of code can gain privileges. So when the code is executing, the runtime linker can provide it with capabilities through dynamic linkage. It will put code capabilities into the GOT of the library. And there will also be data capabilities for global variables in the GOT. Now, the code can also gain privileges by making system calls. So you can call a system call, or the system will call a signal handler to give you some information. Now, of course, there are other pieces of code interacting with your library that will provide you with data buffers or function pointers. And these are also a source of capabilities. Let's deal with each case. So in the case of privileges derived from the runtime linker, our model allows you to enforce a variety of dynamic linkage policies. So policies answer the questions of the form, can library A link against a symbol S defined by compartment B? And there are languages that we can develop to specify these policies, and then the runtime linker can enforce them. For example, we can define a policy that captures notions such as compute only. So if you say this compartment is compute only, then it will not be able to link against any symbol that performs I/O. Second, what about privileges that you can gain from the kernel? Now, the kernel, we make the kernel to reject any system call that comes directly from compartmentalized code. So you cannot just use a syscall instruction to make a syscall in your client code. You have to call the proper libc syscall interface. Now, we enforce this because then if you make system calls via libc, then we can interpose and perform further checks to ensure that your system call is permitted. For example, you can limit what a certain compartment can open with the open system call, or you can limit what a compartment, signals a compartment can handle. Now, you can imagine these policies to be either static or dynamic, and we can expose APIs for you to dynamically register policies. This part of the work is still in progress. Now, thirdly, what about privileges that are derived from other pieces of code? So currently, for data buffers that you pass via function arguments, we don't have any restrictions on that. So we believe that this is more of the programmer's responsibility to make sure that the buffers they pass to untrusted parties, they do not, they should assume that any buffer they pass to untrusted third parties will be corrupted or read in some way. So we don't perform automatic de-sharing of data buffers between compartments. But for function pointers, we do have a solution. So imagine if you pass a function pointer to another compartment, if you don't do anything about it, when the other compartment calls the function pointer, then you will basically run another compartment's code in your own compartment, which will break the isolation very badly. So we have a way of modifying the compiler and linker to address this issue, such that when you pass a function pointer to another compartment and the other compartment calls this function pointer, you can get a proper domain transition back to the original compartment. This is also still a work in progress. Okay, now let's dive a little bit more into the implementation. In this diagram, you can see 3 boxes. The red box and the blue box are 2 libraries. And in the middle of them is the yellow box, which is the TCB. And the TCB comprises the dynamic linker and a number of trampolines, which are code that is generated at runtime by the runtime linker. Now, normally, without compartmentalization, when you make a function call from library A to library B, you will load the code pointer from the GOT and then jump to the code pointer. So this is done by the PLT. Now, with compartmentalization enabled, the PLT will load something else. It will load a piece of code that is, it will load the trampoline instead. And then the trampoline will forward your call to the callee. And the return path is the same. You have to return back into the trampoline, and the trampoline returns back to the caller. So what does the trampoline do? The trampoline updates the register file to isolate the caller and callee state. So, for example, you have callee saved registers that will be preserved by the trampoline. So you can make sure that a callee that does not abide by the contract and mess up the callee saved registers will not actually affect your execution. So when the function returns, the trampoline will restore the correct callee saved registers. The trampoline also enforces properties like well-bracketed control flow. So if you attempt to perform non-well-bracketed control flow, you will be unable to do that. So let me just give you some highlights about the implementation. It's very brief. For example, we have a dedicated stack for each compartment, because suppose we have functions belonging to different libraries. Foo is in the library. When you call foo, it can read and write from our stack and corrupt our local variables. Also, when foo returns, it may leave value capabilities above the top of the stack that we might read. So in our implementation, we allocate multiple stacks, one for each compartment, so that when you switch between compartments, you also switch the execution stack and properly isolate the stack frames for different compartments. So a resulting issue of this stack switching regime is that argument passing does not necessarily work anymore. So if you have a function that takes a large number of arguments, and some arguments will not be passed via registers but via the stack. So in this function f, for example, on the ARM64 platform, you can pass up to 8 arguments via registers, and if you have a 9th argument, it will be passed via the stack. And it doesn't work anymore with our stack switching because the callee will not be able to access this thing, which has been pushed onto the caller's stack. So we have to change the calling convention. We create a buffer and put this argument along with variadic arguments into the buffer, and we pass a capability of this buffer to the callee. So the callee is now able to access these arguments without implicitly relying on the execution stack. Now, this buffer can be located anywhere. It can be located on a one-time use page, so there is no chance of the callee being able to corrupt it or do anything bad. Okay, now let's look at some preliminary evaluation. So this graph represents a benchmark that involves running the gRPC benchmark with asynchronous data streaming. So you have a server, you have a client, and the server is just pushing data to the client, streaming data asynchronously. So it's just sending lots and lots of data in one direction. And you can see 3 lines here. The top line is the ideal performance. It's run using the benchmark ABI without any compartmentalization involved. By the way, the y-axis stands for QPS, which is like messages per second. Now, and the x-axis is the size of each request. So the top line is ideal performance, and the bottom line is when you turn on compartmentalization, you can see a slight decrease in performance, which is expected. But if you apply certain policies to group, so the policy here just groups libraries together, because gRPC includes more than 100 libraries, and many of them are actually supplied by the same vendor and belong logically to the same functionality or group of tasks. So you can actually group them into the same compartment, and this reduces the number of compartment transitions quite a lot. And if you apply this policy, then you can gain some performance back. Next, if we sort of calculate the relative overhead, then we get this figure. I have not included any error bars here, but they should be quite large when towards the right of the graph, because you are dividing very close numbers together with some variance. So as you can see, the top line represents basic compartmentalization overhead, which is hovering around 10%. And if you apply a policy, then the overhead dramatically drops by a lot. So this is the end of my presentation. Any questions would be welcome. Thank you.
Thanks, Dapeng. We have time for a question or two. Ina?
Hi, yeah, thank you for your talk. I'm wondering a bit about this buffer for the spilled registers. You mentioned briefly that you could enforce that it's only, like that it's somehow reclaimed at the end of the function call. Is that correct?
Are you talking about this?
Yes.
Okay, so this buffer, so in the current implementation, this buffer is really just allocated on the caller stack, but it's not safe because the callee can just save up this capability and mess with it later.
Yeah.
But you can imagine an implementation where you have a separate space and you can just allocate a page, put the buffer there, and then throw the page away after the function call returns.
Okay, cool. I guess I had a small follow-up question, but maybe also Robert wanted to say something.
So there was a PhD thesis done by Lawrence Eswood, who's now in Google G-Chips, working on Cherry Things, where he explored the same issue, but I guess in the MIPS context and with sort of a clean slate OS rather than a large existing software ecosystem. And in his PhD dissertation, he describes what he called a slinky stack. He basically gives he has two stacks. He has a conventional stack used for everything within compartments, and then at compartment boundaries, he has this other stack which has sort of use once semantics for frames that need to be shared, and he's able to then perform revocation later. And the allocation process for that is not do memory math, etc. It's just like bump the pointer as you go along, and then he does a bulk revocation intermittently. And for the workloads he worked with, and for the compartment boundaries he worked with, that seemed to work quite well. But of course, the more you envision using this compartmentalization, perhaps the more you care about parsing arguments by reference on stacks. So I think there's not a good understanding there of what the right thing to do is. If you contrast with the Chariot, where the small memory sizes allow a more synchronous revocation model around here, you're able to achieve better temporal safety between compartment boundaries. So I think there's an interesting space to try and understand, but we don't know. And we've been looking at those ideas like from the very beginning of the project. But the problem is like on the system scale in Morello, the rate at which you chew through memory and 64 gig memory sizes and all this stuff, those techniques don't scale. So I think there's room for some good research here. And there's lots of like ideas, right? Something involving linear capabilities and all this and that. They're all really interesting, but those aren't implemented in Morello. So we're trying to stick to the primitives that are present in Morello so we get access to the workloads. And then from that, perhaps we can then spend some time on co-design and figure out what the right solution is, if any, to this problem.
Yeah, that's great. Thank you.
Right.
Thank you very much.